All right, so here's an example. It's an excerpt from my book, The Engineering Dynamics Course Companion, and it's just to do a vector analysis of the kind of joint that causes Coriolis acceleration. And so if you were going to do this based on equations from regular textbooks like the Beard-Johnston selection of dynamics books, this is the approach that you might want to take. It's more of a formal approach. So we have this link AB that's moving, right? It's rotating clockwise at 3 radians per second, and it's increasing its angular velocity at 5 radians per second. And it's 1 meter long. And the pin at the moment that we show, the pin B is located at 0.75 meters away from point C, right? So that position, that can change, as you can see in the dashed line, what it'll look like when it gets to the end right there. So at this moment, we see this motion, and we want to determine the velocity and acceleration of the length in the slot, right? That's increasing, right? So it's going to be this length right here is going to increase. So we want to try to find this. We also want to get the angular acceleration of this piece, right? Whether it's it's probably going to be accelerating down that way, but also we want to get the velocity and the acceleration of it. So what we do is we set up the knowns into angular vectors and position vectors. So we have RB with respect to A. We can see that it's up and to the right, and we can see of RB with respect to C. We can see that it's just horizontal. To find the velocity of B, now this is based only using A as a reference. We take the velocity of A, which is 0, and then we take the velocity of B with respect to A, which we know is the cross product of the angular velocity against the position vector, and we do this cross, and we are able to find that this velocity of B, as we might expect, is going to be down this way, right? That's really what we're finding. But we can also find the velocity of B as it relates to C by the way of the relative velocity of B with respect to C, which now, because it's a sliding joint, not only has this angular component right here, but it also has a relative component, a relative part. So, and we know that that relative part in the position shown is completely in the I direction. And we don't know this, we don't know the amount of this theta dot of this thing, and we don't know the VREL that's taking place right here. These are unknowns. But what we can do is we could equate that VB right here with the VB that we have right up here. And because we have them in the I and the J direction, that makes it really just two equations and two unknowns. And we're able to find that the VREL is going to be this value, and the theta dot R, it really is going to be this. So we're able to get this relative velocity. And from that relative velocity, we are able to go back in and, oh no, actually not true, that because the things are oriented in the J direction, right? We can take the J's and we can equate that J, this J with this J right here. Okay, so there's a whole lot of monkey business that went on in there. And maybe I had too much red. That's what the problem is. We do better with a nice green. Get a nice green. And so we do the acceleration analysis in much the same way. We find the acceleration of B right here with respect to A. And we know this has multiple parts. That it has the tangential part right here, right? So there's going to be a acceleration this way. But there's also going to be an acceleration component that's pointing down towards the pin. And that's going to be this component right here. We could also take the longer equation that I have presented up. I guess it's presented up here. I didn't do the reduced the version that's reduced into one plane, but this is what it would be, and it has these parts into it that equation does, but those are both going to be 0 when it comes to this link. Right, this link AB. The B doesn't have a relative velocity. It doesn't have a relative acceleration, so those parts are 0. And then, so we work out the cross products, and we end up finding we know what the acceleration of B is going to be. Now we do it. Now we take the acceleration of B with respect to C and in the joint up here, and we know that that one is going to have a sliding component. We just found it up here, and we also know it's going to have an angular acceleration. No, we know it's going to, it's going to have an angular acceleration right here that we don't know, and it's also going to have a relative acceleration. So we equate those two things right here. Well, we work out what we can find out, and we leave these unknowns placed. We do know that the acceleration is going to be in the I direction. That greatly helps us. And we also know that the when we get done with the cross product, where did you go? I think it's going to be right in here. We're going to end up knowing that that's going to be in the J direction. That's going to help us right here. So that simplifies things. We could still find it if it was if we had components in the other directions as well. But we're able to set these two things up in two equations, two versions of the equation. We have the I direction right here. Yeah. So we end up with this right here, this I and this J, and then we set it equal to the other acceleration that we got, and we're able to figure out what the relative acceleration is and what the theta dot are going to be from this. So that's like a traditional way of trying to get it. I say traditional way. It's the most common way that people get taught when it comes to acceleration, and it's a pain to do the vector stuff, and it's mostly having to march through. You have to be a little bit disciplined and just going through and doing the being a little meticulous. Quite often, now I should mention that my examples, what I like to do, and I don't know if it helps or not, but it's what I always wanted, is I don't skip steps. So I try to include every single step that gets done in there. It makes the thing look very messy, so I think there's the downside of that is it makes things look maybe more complicated than they are. But on the other side of it, what I'd found and what aggravated me, and the reason why I like doing this, is that I'd done a lot of engineering reading and taken engineering courses where there's a lot, they make it look overly simplified, where they will just jump from a couple things and they don't bother showing you the cross products and that type of thing. Or maybe you don't need to do it all the time, but I think it's good to, even in a simple example, to show these things. So we're going to compare that example to the next one coming up. And I guess I'll do that. I kept doing it. I'll keep this video going. I'm getting very tired. But if we do the same problem now with a vector loop method, and I took a couple liberties when I did this one with using a little bit of a different conventions for things. For one thing, I decided to make my vector loop counterclockwise. I kind of liked that better in terms of my numbering. In order to make a loop, I included a ground link here at C, and I also labeled them, use capital letters because that made a lot more sense to try to keep them lettered the same. So here's my vector loop. Going this way right here, we're traveling along A in the positive direction, then we go backwards through B, so we have negative direction, then we go positive through C, and if we write this out as it's vector complex notation right here, and we take the derivative of it, you'll notice that C is going to go away because it doesn't change. Its angle doesn't change, and its magnitude doesn't change. But when we take the derivative of A, we get the same result we normally get. But when we take the derivative of this B portion, vector B portion, we have a B dot and we have a theta dot. So there's going to be where the slip comes in, where it plays a part. If we take another derivative of it, remember we have to take every single part. We have to do derivative of every single part that's going to vary. So I guess I decided to go with the theta double dot to start with. And then we also did the E, so that's going to bring down that theta and bring it to a theta double dot. It's also going to make it negative because there was an I. By the way, I decided to use I's instead of J's when I did mine. And then when I went to the so I don't think this should not be there. Yeah, so I need to make this a B right there. Yeah, that's it. That should be, is that true? Let me double check on this right here. I think I screwed something up when writing this out, which is totally a normal thing for me to do. Oh yeah, I got you. Yeah, okay, yeah. So that was just taking care of A. Then when I go over to B right here, I guess I decided to go with this guy first because I went my B theta double dot. Yeah. And then, so I took care of him. And then I also, then I went to this B guy right here, and he's got a B double dot. And then, in the process, 2 times is going to happen where we're going to have this B, we're going to take the derivative of this B, and it's going to be a times a theta dot. And then it also was going to happen when we had this B dot, and we took the derivative of that. So that's why it had a 2, and it happened twice. And then we also, lastly, we're going to have, we're going to take the derivative of this guy right in there. That's true, yes. And that's going to bring another theta dot down and an I down, and that ends up changing the sign. So that's the Coriolis acceleration right there. So that's just walking through so you can see what all those parts are. Now we just take, and to solve this thing, we just employ the Euler identity. So in the velocity for this guy right here, I plug both of them in. I distribute them out so that I do it in 2 different steps. I showed both of the steps in there, and then I separate out into real and imaginary parts, and then I put in the unknowns. And what I'm left with is a B dot and a theta dot as my unknowns in these 2 equations. And 2 equations, 2 unknowns, I'm able to solve for my B dot and my theta dot. And you'll notice that we get the same thing as our VREL and our theta dot here are 2.6 and 2. And and by the way, I got it as clockwise right here, so I also show it as a negative right there, so it ends up being clockwise. I believe so. Yeah, I'm using negative as the convention, for clockwise. So counterclockwise is still positive. So a negative result there does give me confirms that I'm getting the right answer. So this is, I just repeated the acceleration thing that I got up from above here. So now we go ahead and to solve this one, we plug in the Euler identities in here. And this is just showing this off long, right? So this is all just one equation of just, just when I did a carriage return. So you could see all the different parts as we're coming through here. You could follow along and see how I put them in there. And then I distributed them, right? So I took all those i's and multiplied by all the things and turned all the signs around. Did I do the signs in this? Yeah, I did. Okay, so all the I squares turned the signs. And then I separate these into real and imaginary. And then I could plug in the unknowns, the knowns, and what I'm left with is a theta double dot and a B double dot. There's your theta double dot and their B double dot. And then just a little bit of algebra, and I'm able to find my these 2. So these are 2 different methods. One is a more traditional or more common way that gets done in dynamics, and then we also have the vector loop method, which is, you can see, is a very powerful method to work on things. And it would really be good if we had enough time in the semester that we would get to this point, and then we could start approaching non 4-bar, non-crank slider problems, right? That's really what we want to do, is want to approach other kinds of problems instead of just always doing a 4-bar and always doing a crank slider or slider crank, or in this case we have an inverted. So here's like another example that I'm going to do now for the inverted slider crank in the next video that I probably will make tomorrow because I'm very, very, very tired. So thank you for your attention, and good night.